Good afternoon. Welcome to the Face of the Earth Keynote Lecture number 3. We had keynote lectures on the rocks, water and life in the last 3 days. And today we have the keynote lecture on the atmosphere, face of the Earth and the atmosphere. And particularly pleased to welcome today's speaker, John Burrows, to lecture on this topic. And he is himself a Willem Birkens medalist of EGU, and I'm really looking forward to the talk on the face of the Earth and the atmosphere. Please.
So, thank you very much, Gunther, and thank you very much all for showing up. It's nice to see friends and colleagues for many years coming here to listen to me. You may be disappointed, you may not be, in what I'm going to tell you about. This is the sort of lecture that you get invited about 3 or 4 months ago, and you think there's plenty of time and nothing, yeah, it's a good idea. And then actually when it comes down to it, my God, what should I actually talk about? Because I'm definitely being taken out of my comfort zone. And anyway, the storyboard or line of this talk is, I'd like to take you from the birth of the universe to the Anthropocene. And then I'd like to give a success story. And after this, I would like to talk about tropospheric chemistry and a little bit about climate change. And then I think I'd like to just go a little bit into my own area, which is these days the new research frontier, and this is the global observation of the Anthropocene from space. So, what happened? Well, at something like 13.8 billion years ago, we are told, or we are informed from our top physicist, the universe started. And from that point in time, it's eventually, as you can see on the right-hand side, some thinkers showed up. But I don't know when life first came into the universe, but we know when it came onto Earth, and this was some billion years after the start of the solar system, and about 5 billion years before present, the basically dust and gas spinning together from previous nebulae, etc., came together and started to form our solar system, flattening eventually sufficient gravitational activity that we form sufficient close, dense packing to form a star, and our star was born. So that's when we have the sun. And then on the edges of this spinning new galaxy forming, basically, or solar system, we're actually, the heavy metals cluster together and we start to form the planets. And the inner planets, including the Earth, formed with a rocky surface and molten cores. And then we have the gas giants a little bit further out. And just as an example, this was a pretty rough time if you were a living species at the time, because this is sort of the artist's vision of the creation of the moon. So there's a lot of collisions going on, and probably a large hole knocked into the somewhat embryonic Earth. And moon, possibly a second moon form. I think there's quite a lot of, that's not my area, but I think that's a very exciting part of our science overall. At this stage, here's an artist's impression of the first atmospheres. And just looking on the right-hand side, it's interesting to see that the moon has basically no molten core, but the Earth does, Mercury does. And this is also a key, obviously, to forming a magnetosphere when you have charge flowing and you form a magnetic pole. So the core region is very hot, actually even hotter than the sun apparently, and the core is largely liquid metal. But the high pressure makes the inner core turn to solid despite the high temperature. Okay, so the heat is a combination of energy. In fact, actually we get very little of that heat. We don't use it much at the Earth's surface. That's a surprising thing. Most of our energy is coming from the sun. Now, let's have a look at the very first atmospheres. We talk about in our courses 3 atmospheres. But prior to something like 4.3, we have 3 billion years ago, we have very little idea about, or not too good idea about what was actually happening. But using various records that we've been at and proxies, we've been able to put together the following picture. Now, what you can see is a dramatic change, and as a result of this, we go from really a reducing atmosphere with methane and ammonia, just going back to that picture on over here, this kind of not very healthy place to live in, to this new atmosphere. Now, actually, this is basically, this big change is the result of life. And the first life, let's just make a comparison with other planets. Okay, and as we know, those of us who teach this subject, the Earth is currently very different. So just going back, we've gone from a methane and CO2 atmosphere similar to those of our neighbouring planets to one that's very different. And one key issue to have an atmosphere, which of course I have to state, is that you have to have sufficient gravitational force, and the temperature of the gas has to be sufficiently low that you don't exceed the escape velocity. So if molecules are moving fast enough, they can leave the Earth. So in the formation of the Earth's atmosphere, we've got to go through a couple of critical stages before temperatures are getting to somewhat similar to our own. Okay, so if the molecules are moving fast enough, you have a Boltzmann or Maxwell-Boltzmann distribution, and the top end is going to fly off, or possibly all of it if it's hot enough. So this isn't the situation in our own atmosphere where only hydrogen, possibly hydrogen fluoride, or excited molecules which are photolized can actually leave us. Anyway, we go from this reducing to essentially an oxidizing atmosphere. As a chemical physicist, physical chemist originally, it's amazing that you've got so much oxygen in the atmosphere because it's a free radical. It's not surprising that you have combustion. It's got 2 unpaired parallel electrons. It's an extremely reactive species. So how come we've got so much of it? And how come the others don't? Now, this is what Jim Lovelock disagreed with on NASA on the hunt for life on Mars. I think we're now back to the stage that we're hunting for old life on Mars, but certainly just looking at the planetary atmospheres, what you can say is that Mars and Venus are in reasonably good chemical equilibrium, whereas the Earth's atmosphere is definitely a biogeochemical system, some sort of stationary state or equilibrium. So it's being driven by the emissions from the biosphere, and biogeochemistry plays a dominant role in our modern world. How did this all happen? Well, after life was brought here, or came here, or was formed here, there's obviously great ideas about how that actually happened, but I'm not going to say too much on that. We have the first simple cells, followed by already 3.4 billion years ago, cyanobacteria started performing synthesis. Now, they're still doing a very good job at this, I'm glad to say. And actually, we really like to measure them from space in ocean color and other places. So the cyanobacteria have been a very successful species. More complex cells started forming, eukaryotes, and respiration started happening, but there still wasn't very much in the atmosphere. The first land plants formed about 475 million years ago. First insects showed up 400 million years ago. And 360 million years ago, amphibians, then later reptiles, then more recently mammals, birds, flowers. And for over 60 million years, the primates first showed. For the last 20 million years, some relatives of ours showed up for the first time. But we're really only an eye blink. Mankind has only been for a very short period of time on this earth. Yet, I'm going to tell you about it's now dominating the situation. So let me just jump ahead. I'm going to bring that together, and this is a particularly important graph because it shows the mixing ratio, basically, of ground level oxygen concentrations as a fraction of the present atmosphere. And what you can see is it took quite a long time to build up a sufficient amount of oxygen in the atmosphere. And evolution is obviously playing a great role in this. And a very important aspect of the formation of ozone, for those of you who don't know, is that ozone absorbs in the UV. So we have the solar radiation from the sun, which is essentially a black body at 6,500 Kelvin or 6,000 Kelvin or so, emitting primarily a maximum around 5,800 or 5,580 nanometers. As a result of this, you have a UV tail. You have hotter stars with much more UV light, and I'll come back a little bit to that, but basically, this UV radiation photolyzes oxygen between about 150 or something and 220 or so nanometers in the so-called Schumann-Runge bands in particular, and creates oxygen atoms. Oxygen atoms then react with an oxygen molecule and form ozone. This ozone then absorbs in the UV strongly between 320 and 200 nanometers. And that's the key issue which enabled species like our own to leave the ocean and to start being able to walk around, because we no longer had to carry a UV absorbing layer, because our DNA has an absorption around 290 nanometers, and if this is activated, it's likely to cause skin cancer. Okay, that's the basic old issue of ozone and UVB at the surface. Certainly, UVB at the surface is modulated by cloud, but the first protective layer with respect to UVB is ozone. Obviously, the shorter wavelength UV is being knocked out by O2, and the very short wavelengths by other species. So this is a key. So the combination of where we are now, and this is why people like Lovelock proposed the Gaia hypothesis, where you have the idea that the biosphere is trying to maintain the conditions on planet Earth to sustain itself. There's been the sun has significantly darkened since the first living things were on this planet, yet we've had rather stable conditions. So this is a key sort of idea which is very much still active. In terms of looking at the more recent past, from the Holocene back to a few million years ago, our geological friends always put the graphs in the opposite direction. So this is years before present going that way. But what you can see is, if you look at these very clever measurements, and I'm taking these European measurements, but there are many very good cores which are giving this information. What we're able to see is the variation of CO2 methane, and the delta D, for example, is an indication of temperature. So we're able to, basically using proxies, get temperature. Delta oxygen is one way of doing this, and it's essentially equilibriums that you're looking at. And you're able to, by taking these small amounts of air in the ice cores, determine the concentrations of these long-lived species, and thereby create a whole ecological history for us. And what's fascinating is the amounts that things are changing by. And if you look at the methane and the CO2, you'll see that things are very much different to, in the past, to what they are nowadays. And that's an important clue to this new age. What about the physical structure of the atmosphere? Well, looking at the temperature, we really like temperature. Coming from the top, first of all, we have the exosphere, so that's essentially outside of the Earth, but then the thermosphere. That's changing as a result, or its temperature is changing as a result of the shortwave radiation from the sun modulating over the solar cycle. So that changes the temperature, so the active sun has a much higher temperature, and this is essentially being heated by the absorption of solar energy. We then have a region of what you might call normal atmosphere, in that temperature is falling off with altitude, and that's called the mesosphere. And then we go into the stratosphere. Now, the stratosphere is the region where the ozone is, and this was actually discovered only 110 years ago in Berlin and in Paris by the first dedicated balloonists, Ashman in Germany, and I have difficulty saying the French name, but Thierry de Borch, I think is the right way to say it. But anyway, these guys rose up on the balloons and actually measured temperature the first time and showed that it was very strange that the temperature started to increase. So they discovered really the tropopiles rather than the stratosphere. And this was a key part of our understanding. What's happened now is that we're now talking about being in an Anthropocene. And I'll come back to this one more time later on. But if you consider human beings, they were essentially hunter-gatherers till the Neolithic Revolution, where you had 4 to 10 million people on the planet, already quite a successful species. Using essentially biofuel and a little bit of coal, wind, sun, this rose to 1 billion around about the time of the Industrial Revolution, which started close to my birthplace. And since then, well, it's just been dramatic because we now have 7 billion people, 50% of which are now, or more than 50% are living in urban agglomerations. And we're expecting to reach in 2050 of the order of 10 billion. And 75% may be living in cities. Now, this is having a huge impact on or the industry of these people and their use of land. Is having a huge impact on the emissions to the atmosphere. And this is why this term Anthropocene has been very much popularized by my former mentor, or my mentor and former boss, Paul Crutzen, although originally proposed by Stürmer. And basically, this is a very useful concept because I think it's telling us that we should go from the idea that we're hunter-gatherers to some new in the Anthropocene, we have to think of it in a different way. This is like guardian of the planet or something. We have to find a new way to live and to develop ourselves in order to obtain sustainable development. And the jury is very much out whether we'll do this. Now let's just go a little bit more into the detail. Here now you can see some trace gases, obviously the nitrogen and the oxygen. The nitrogen, of course, coming from a whole series of sources, but in particular also from bacterial decomposition of, for example, ammonium nitrate. So we're also disturbing the nitrogen cycle since we invented the Haber-Bosch process. The nitrogen problem, which is on the one hand sustaining our food production, we've never fed so many people before, along with pesticides and the rest of it, is actually putting a huge amount of ammonia and also NOx into the atmosphere from soils. Through fossil fuel production, we're massively increasing the amount of oxides of nitrogen into the atmosphere. And of course, through fossil fuel combustion, we're of course releasing methane and creating, by burning coal and methane, CO2. So we're already on that. You can see on this plot, we're in a very different ball game at 395 to those pictures that I was showing from the Holocene, the recent Holocene. And of course, it's very interesting. There were two, a sort of lucky break. 1957 was the year, or the geological year, or geophysical year, IGY. And in Europe, Dobson and Brewer and others decided to try and get Dobson spectrometer networks measuring ozone, and Joe Farman actually installed the instrument down in Halley Bay. And Revell in California at the same time wanted to have CO2 measurements. And the famous CO2 measurement curve from Keeling, the Keeling curve, began together with the Dobson ozone measurements in this year of 1957. And you can see gaps in the early record because people were running out of money. They didn't know why they needed, whether or not they'd be able to fund them anymore. But what you can see here from Mauna Loa, of course, is that the seasonal change, so what happens in the carbon cycle is that leaves fall in autumn. During winter, not too much happens. Then in spring, they decompose, CO2 is released. But then the growing season starts, and in the northern hemisphere, carbon is pulled down. However, we're not pulling down sufficient to be able to take out the amount that we're putting in extra from burning fossil fuel combustion. And this is this wonderful record of CO2, which is a major importance in our science. You can see changes in the curve, which gives us some confidence that this is changes of economics, or when you have an economic crisis and you lose a bit less, or impacts of a Pinatubo, a large explosion where you cool the atmosphere a little bit. This impacts on the growing season, obviously. And El Nino, the southern oscillation of winds, this change of temperature in the Pacific has influence on it. So we can pick out all those things, and we're pretty confident about what we know what's going on. Of course, the question is what will happen in the future and how we move on. What process regulates the CO uptake? Well, you've got certainly CO2 going into the ocean, but as the ocean's surface rises, we expect that to be less. Eventually, the ocean will win out, so the oceanographers eventually decide what climate change is. But in the short term, the land surface is highly variable and very dependent on changing conditions like precipitation and desertification. All these sorts of processes are going to determine. Also, the leaves, when they open their stomata, that's very sensitive to temperature and humidity. So you change conditions, you're going to change the amount going in there. Can we predict that? I don't think so. I think we have good ideas about it, but it's a very challenging target to be able to predict exactly what's going to happen and where. So we really need to understand regional climate. For example, the temperature has risen much faster in the Arctic than anywhere else on the Earth. The Antarctic's a bit of an oddball, and these are very disturbing matters. In the past, we had polar amplification in previous climates, going back to that data record, but then they were actually in both hemispheres, as far as I understand it, being a non-expert in that area. But so we've got huge issues to understand why there are sensitivities. For example, there's a huge amount of carbon stored in the permafrost, and there are different ideas as whether that will come out as temperature rises and how it will come out. So we have large worries about the future, and we need really good measurements to do these things. So what's going on? We've got the total amount of anthropogenic there, and we were able to separate it into land uptake and also ocean uptake. So what are the processes absorbing almost half of the CO2? As I've explained some of those, why does the amount of CO2 remaining in the atmosphere change from year to year? It's because obviously we're putting more into it, and what will happen in the future. Okay, we've now got into the world of IPCC, the Kyoto Protocol and its amendments, and we're looking at these types of cartoons which explain carbon cycling in the atmosphere. It's obviously very complicated, but this is where we're looking at the bottom of the atmosphere and the surface and how they're interacting together, and what are the fluxes going up and down. And there we need really good measurements, and we need to understand these things in the future. Much better than we do now. Okay, just noting that where there is a very small amount of CO2 in the atmosphere compared to where all the rest of the carbon is, but small changes of that we've basically got a biogeochemical equilibrium in the atmosphere, so we need to change it a little bit, and we're obviously going to go up or possibly go back down. But this is the 100 minus 99 problem. We're looking at the one unit that's left over in the atmosphere. We, of course, have natural global warming from water. The Earth's atmosphere, as viewed from space, is about 40 Kelvin cooler than that of the surface of that order. And the vast majority of that difference between current surface temperature or surface temperature prior to the Anthropocene and that outside it is the global warming of the hydrological cycle and water. So this is not the new thing. What we're talking about is 2 or 4 degrees extra, which is coming from our changes to CO2 and methane. Now, that's why this term Anthropocene, and I hope you can read all these things, has been created. But what we're seeing in this Anthropocene is a remarkable increase of population, GDP, foreign direct investments, CO2, N2O, also coming from the bugs destroying ammonium nitrate, and of course atmospheric methane on the top line. And then all these other things, including somewhere on there is McDonald's restaurants. So we're seeing huge increases, and that's why we think, at least from those of us who support this sort of concept, we're hoping that the geologists will eventually decide when it really started. There's some argument about whether or not you should have the Neolithic Revolution or the Industrial Revolution. But the point is, if we are in this new age, I think it puts some pressure perhaps, or maybe politicians should think a little bit about why we're calling it the Anthropocene and what the consequences of that are, and maybe change our hunter-gatherer mentality. Okay, because the problem is, if we look at it like this, in the case of the chlorofluorocarbon compounds, which I'm going to talk about briefly, which we put into the atmosphere the first time in the 19th century, and they built up, and Lovelock measured them in about 1972 and said they're about equal to what has ever been produced. And then later some other people came and said where it's going. I'm going to talk about that in a bit. But essentially that was a new molecule or new set of molecules in the atmosphere created by the chemical industry, created by Kevel people. It's funny, the same guy created both the chlorofluorocarbons and lead tetraethyl on a commercial scale for use in the automobiles as an anti-knocking agent. If you remember such things, the older ones of you, that you had knocking in the car. This is the non-perfect combustion. There used to be a lot of work going on about getting combustion perfectly. Possibly there still is in Formula One. But the point on this is that this guy did the same things, both of which I think are basically pretty bad. One led to lead being quite a problem in cities, potentially affecting children living close to motorway intersections. And at the same time, they started creating these chlorofluorocarbon compounds, which were just great because they're not poisonous, and they enable us to, we can use them in all sorts of they're great refrigerants, they've got great properties, except for the fact, as we'll hear, that they're not very good for stratospheric ozone. But that's a sort of special case, and it's easy to pick out. But in fact, the more general problem is that we are adding a lot more of something, or taking something out maybe, from what is already there. Changing the land surface, for example, maybe changing deposition rates, increasing them, decreasing them. But in general, we're tending to sort of chuck a lot of more stuff in, like SO2, like ammonia, like NOx, also non-methane hydrocarbons. And this is causing us a lot of trouble. So this coupling is the problem is we're shifting the system, and we don't really know where we're shifting to it from a biogeochemical standpoint. So that's what we are doing. Okay, now I'm going to go to some key interesting developments and do a little bit of history. This is supposed to be a lunchtime talk, so you should have brought your brown bags along, and you can actually drink and whatnot in the meantime. But a particularly key development has been this development of our understanding of ozone. And this goes back to the birth of chemistry, as opposed to alchemy, in the 17th and early 18th centuries. And clever scientists in Oxford and Cambridge and elsewhere around the world, in Paris, started trying to measure the gases and being able to separate them for the first time. And so they were learning lots of exciting Gay-Lussac's law and all this kind of stuff. But they were able to identify these gases. And in fact, at the same time, they'd also recognized that we have pollution. In fact, in England, Edward I already had some laws to try and prevent pollution in the 13th century. And the smoke in London was well known in Tudor times. So you had local pollution. So the idea of pollution being local was not so new. And here are some people, great thinkers and scientists thinking about it. Leonardo da Vinci, John Mayo, in Great Britain discovered that air is composed of fire air that supports combustion. We'll come back to that in a bit. And foul air that does not. Okay, that's basically nitrogen and oxygen. Carbon dioxide discovered by Joseph Black. Nitrogen eventually identified unambiguously by Rutherford. The fire air was isolated by Scheele and Priestley and Lavoisier. And Lavoisier actually gave it the name of oxygen. And noble gases. So this was a great time for the rich hobbyist scientists. They were doing some great work. They were basically all doing it on their own time and their own money, one way or another. And Strutt and Ramsay could also be put into that class. They were able to do their work and actually identify the noble gases, quite a difficult thing to do at the time. So brilliant experimentalists. Now, what about the discovery of ozone? So first of all, actually, van Marum had discovered this funny gas, but then Christian Friedrich Schönbein this smelly gas, as it was called, ozone, which you're able to create by electrical discharge. And you have the Siemens discharge still today apparatus which makes it for you. So you put an electrical discharge through oxygen and it makes oxygen atoms and they react. Also electrons, it's a bit more complicated than I'm saying, but you basically produce ozone. And Schönbein actually had a very happy and good life, having actually announced this discovery in Munich. He then created papers which measured it. And at the time, ozone was thought to be a healthy thing. And so he made quite a bit of money on the side, actually measuring. It's a little bit like radioactivity used to be thought as a good thing when you went on your holidays. So ozone was wrongly actually identified at the seaside, but it has a somewhat similar to smell to methyl chloride, methyl bromide, which is coming out of the ocean. So he's had quite a happy life and was very successful. Okay. What about the first atmospheric observations? Well, it's also quite a long time ago. Herzog and also Levy made some really great measurements. This time of discovery, and Paris played a great role. The Montessori laboratory has very important measurements. What about the optical properties? Well, Cornu observed this ultraviolet or sharp cutoff at 300. This is what we now know to be the Hartley or Hartley-Huggins bands of ozone, and Hartley was the first one to identify that this stuff must be in the upper atmosphere because it couldn't get any light through. I mean, we've forgotten, of course, Fraunhofer invented, or one of the inventors of spectroscopy. These were the tools that came to scientists in the 19th century, and they started looking and then discovering these things. And Strutt actually showed that UV absorption does not happen in the lower atmosphere. So, or not significantly. In comparison, it does in fact happen, as we'll see later. Huggins reported several longer bands, which we actually use now for measuring ozone as a community. And these bands are attributed by Fowler and Strutt to the presence of ozone. In 1920, Fabre and Buzon used absorption properties to deduce the thickness of the ozone. They actually got a pretty good value, 3 millimeters STP. That's the column when you reduce it to 1 atmosphere pressure, which would be nowadays 300 Dobson units or so, which is a little bit less than what you typically have probably today. I don't know, we've got about 400 or something like that Dobson units. A Dobson unit, as you'll see, is related to this mercury scale. Okay, and there we have, of course, Dobson. So he started and had a very long and successful career, started measuring in the 1920s using an improved spectrophotometer. And this photometer, as I've already said, was 70 of them were created in the post-IGY time around the globe, and we had this record. And he had a very strong influence on atmospheric science, together with Brewer in particular, and a whole host of other people, too many to mention. But here's his first apparatus, which is now, and you see it's made out of wood. And actually, he was still working when one of my other mentors, Richard Wayne from Oxford, started in Oxford. And Richard used to make ozone for him, and a student would take it up in a glass bulb on the bus to Boars Hill. Now, if you know anything about pure ozone, it's extremely explosive. So there's always a question is why it didn't explode on the bus. But the student who was taking it up was actually a Jesuit priest. So maybe he had somebody looking after him. Anyway, ozone observations continued. Spitzbergen and, of course, Götz and Deutsch created this Arosa record. And for a long time, the Arosa measurements were really important, and at Arosa in Switzerland, we saw actually, together with the TOMS instruments, this decaying mid-latitude ozone, which I'm going to come back to in a minute. So you see great variability. There's all sorts of exciting stuff in it. Dobson was very keen to use ozone as a measure of the tropopause, because obviously, as it goes up and down, he could consider it to be, in large part, conserved in the lower stratosphere, which it is most of the time. We'll see some differences with respect to that. What about the ozone conferences? These were very important. Actually, in 1929, at the first ozone conference, Sidney Chapman, who, like myself, went to Trinity College, Cambridge, I think he's done a little bit better than I did, but he actually proposed the first mechanism by which ozone could be formed, and he recognized that oxygen, as I said earlier, is photolyzed, O atoms are produced, and then a termomolecular reaction, so that's quadratically dependent on the inverse of the pressure. So as you go up, or as you go down rather, that increases dramatically. So you have, and he considered the loss reaction would be O plus ozone. That turned out to be wrong, but he had a steady state system, production being essentially photolysis of oxygen followed by a rapid reaction to ozone, getting much more rapid as you went down, and the loss of ozone by a reaction of oxygen atoms with ozone, which doesn't take place. This is his scheme. And there's my Tesseract de Bort, an Ashman who invented. And this wasn't very long after that we had these theories, so people were moving at a great pace. What about photochemical theories then? How could we explain it? How could we explain this extra loss? This was very much still academic realms. It wasn't really considered as very important. But the first people to make a breakthrough here were David Bates and Marcel Nicolet. At JPL after the war, they, through recognizing that Meinl had observed OH in the upper atmosphere. Now, OH in the upper atmosphere comes through the reaction of hydrogen atoms with ozone, and it makes an excited OH, which is vibrationally excited and then emits. So at night, in particular, or close to dusk, you can see, and this is still something we use nowadays for measuring the temperature of the upper atmosphere, the OH rotational temperature. But they figured out where must this be coming from, and then went further to say, okay, if H reacts with ozone and makes an OH, and an oxygen atom reacts with OH and makes an H and an O2 back again, we're going to have the equivalent of an ozone plus oxygen atom, so-called odd-oxon destruction. Somewhat later, then, John Hampson suggests that similar processes can destroy ozone in the stratosphere, not just in the mesosphere. So this is what we had to begin with. Now this is, we're now up to 1996 or so, sorry, 1966 or so, so only 50 years ago, and progress has been very rapid, and progress has been rapid because the impact of humans, as shown on this cartoon, through the emissions to the atmosphere of long-lived species, which are then transported to the upper atmosphere. For example, this is what we understood then, but then came the first discussions. Paul Crutzen recognized that nitric acid was present in large amount and wondered where that was coming from, somewhat similar to Bates and Nicolai thinking about OH. And he figured out, okay, well, there must be a nitrogen cycle, and he published this around 1970, and also thought maybe that aircraft might be a problem if they got up there. Harold Johnson, in Berkeley, thinking similar ideas, came up with the idea that supersonic aircraft would be a big problem. Now, this is actually where these people both had great influence on my life. Harold, because in Britain, of course, at the time, together with the French, we were building Concords, and Concords were then threatened by these environmentalists in the US who were saying they're not a very good plane. In fact, it turns out they weren't very economic either. But so there's a big campaign, and in fact, my graduate studentship at Cambridge was paid by the Royal Society to look at the laboratory kinetics of HOX reactions, and one of the reactions I studied was HO2 with NO, and that turned out to be poorly measured, and Carl Howard in Boulder and ourselves in Cambridge measured this to be much faster. And this actually changed the lower atmosphere to being, as it turns out, production, lower stratosphere, NOx produces ozone, as we'll see also in a similar manner to that in the troposphere. But at about somewhere like 28 kilometers, it turns over because there's a competition between O plus NO2 and O plus ozone. And once you react O with an NO2 and you make an NO plus an O2, you have, as we'll see, a catalytic cycle as shown here on the inside, which is then removing ozone very rapidly. Now, within a few years of this discovery, and a whole host of work to do with, obviously, aircraft industry and future fleets, Then Mario Molina, it's actually Rich Talarski and Ralph Cicerone were working on chlorine and had recognized if the chlorine was there, you would also have a chlorine plus ozone making ClO plus O2 and O plus ClO making a Cl plus O2. So again, an odd oxygen cycle. And but they were really thinking about the shuttle, or a little bit about shuttle exhaust and stuff like that, what was going on. But Mario and Sherry had known of the work of Lovelock, what I said before, about measuring the amount of chlorofluorocarbons in 1972 and saying, well, it seems to be about as much as has ever been produced. So Sherry's and Mario's idea was to look at where it's going, and then they came up to their surprise that this could go up into the stratosphere, be photolysed or react with O singlet D and produce massive amounts of active chlorine, as we call it. And shortly thereafter, so that was 1974, was a very big year, and this can reduce a lot of ozone, and it's a lucky break that we didn't put as much bromine in, as I'll say in a minute. But the bromine idea was also because we're producing methyl bromide. There's a lot of people here in the audience who measure that. And lots of halons, which are also non-man-made or man-made compounds, which are used in, for example, fire extinguishers. They're more expensive. The point about we had a lucky break here because bromine compounds were more expensive than chlorine. But if we'd produced the same amount of bromine going up into the stratosphere as chlorine, we'd have removed the whole of the ozone layer, more or less, because this cycle is 10 times more efficient than this. About one chlorine removes about 1,000 ozones. So in this cycle before, you form HCl and chlorine nitrate. So there was a lot of work done in that period to establish what was going on about exactly how effective these chain reactions would be. And we came up in the end of the day, it would probably be about 70%, 30% dominant for the amount of ozone. And that was the situation about 1980, where we thought, okay, we're going to have to stop the amount of chlorofluorocarbons. But then a few other things happened. And first of all, I want to jump back now to understanding the dynamics, okay, because obviously this is a very complicated physico-chemical system. I was mainly talking about the kinetics there of the chemistry. Okay, Brewer and again Dobson made great strides, and Dobson, by making measurements of water and recognizing that within an aircraft actually an RAF aircraft in the early 1940s, seeing that the amounts of water could not be coming from locally. They had to be transported effectively from the tropics. So Brewer-Dobson circulation explains these things. So both of these guys made significant contributions to this. And the Brewer-Dobson circulation, here you can see some pictures of, at the bottom, we're seeing what we now call the tape recorder from Halo. This is on the right-hand side, this is altitude versus the water vapor mixing ratio. And you can see how it goes up, and basically in the tropics, the idea is that you have upwelling, and then it goes into the winter hemisphere and comes down at the poles. In fact, it's more complicated than that, and there are many branches of it. But essentially, the idea is you're injecting water, and also you're making ozone in the tropics, and then it's being transported northwards. And dynamics became a very dominant theme, and here are two heroes of this field, Jim Holton and Michael McIntyre, who came up with understanding these complex flows. It's the fluid dynamics of the atmosphere is really complex. It's very beautiful to look at. You have a whole host of complex issues. But one reason why this came up then is after we're understanding, here a cartoon showing how we understand the dynamics of the atmosphere, including the wave action. So when waves break, they put momentum there, which is pushing the ozone and other species north or south in the appropriate summer or winter hemispheres. These are the type of pictures we have. The current, this is about 20 years old now, this is the current picture which is still pretty accurate, from Holton and Partners, where we have this middle world, as he called it, or they called it, including Peter Haynes from Cambridge, who actually made this diagram originally, I think, whilst working with Jim. This sort of wave-driven, so we have this sort of concept of ozone now being moved around, and we're beginning to understand it. What was a complete shock was, of course, in 1985, was that we suddenly had an ozone hole. And here's the team at Halley Station, and this was Farman, Gardner, and Shankle. It's actually, I think, John who first noticed some of these odd things. And they had, of course, a lot of measurements, so they were pretty clear that after 1980, they were rather cautious about showing this, but they were able to show these curves. They certainly recognized something early on, but you could see in October over Halley, you had this unexplainable loss of ozone, and they suggested at the time that it must be something to do with chlorine, and that was bang on. And then we had lots of theories as to why ozone in the pole could be removed so quickly. Susan Solomon pointed out activation on PSCs as an important part of it. Paul Crutzen was also involved in this. Mario Molina pointed out that under these conditions, when we understand the key issue was these polar stratospheric clouds, which a bunch of colleagues, which previously were just thought to be something beautiful. They're called polar stratospheric clouds. You can see them because they reflect the sunlight. They're about 26 kilometers, but these are actually in large part nitric acid trihydrate. So in the cold winter night, you take stuff out of here and produce take nitrogen out. This enables a runaway cycle in chloride called ClO plus ClO. I'm going to show it in a minute. And actually, Mario first pointed out that one. And there's also a cycle. So this is this one here that you make a dimer of chlorine monoxide, and then you can actually photolyze it, and that as a similar bromine. Okay, so that's our situation. Let me just go back and just say that we currently understand it. And that situation from about 1990, we've just got an ozone assessment going on. It's basically the dynamics is changing, and that's why an interaction with climate change is of concern. What will happen? Actually, we think we may have a super recovery, because as you change the temperature of the stratosphere, as you cool it as a result of CO2 emitting to the atmosphere in the stratosphere, you actually increase the O plus O2 plus M reaction. Okay, but actually the Montreal Protocol has been successful, and we're beginning to see ozone coming back, but it will take another 30, 40 years before we reach 1980 levels. And for these works, our community was honored by our champions winning the Nobel Prize in 1995, almost exactly 20 years ago, 19 years ago. Now, what about tropospheric ozone? Basically, Los Angeles smog was first observed in the late 1950s. Los Angeles is very dry, there are a lot of emissions, it was very high standard of living, and basically within a short period of time, we understood locally that hydrocarbons, NOx, and sunlight were the cause of this smog, which was ozone, species like pan, peroxyacetyl nitrite, and a whole load of toxic species. And OH radical was playing a very big role. What was surprising is this type of smog has gone around the world, but also the earlier discovery of winter smog with particulate matter, and we've been seeing this year in winter in Beijing, we had these really awful conditions. It's been bad there for a long time now, but it was particularly bad. What was strange is that we had very high levels of pollution in Paris only a month or so ago. And this is very definitely impacting on human health, agricultural yield, food, etc. However, this was when I started work, this is what I understood in global tropospheric chemistry, essentially ozone coming out of the stratosphere and going to the ground and being deposited. This is the situation now, which I'm sure you all understand, just looking at it straight away, but what you have is large catalytic cycles here making ozone and catalytic cycles removing ozone. And these are created by the emissions here at the bottom. And so if you have the right conditions, it's actually the RO2 plus NO and HO2 plus NO, which are critical reactions because they make NO2. NO2 is photolized and makes an O atom, makes an NO back, which can make more NO2, and that O atom reacts very rapidly to form ozone in the troposphere. On the right-hand side, you have aerosol, which we were just looking at before, and the huge input of SO2 makes the reaction with OH, H2SO4, and the aerosol precursor. So this is the thing we have to understand now in particular. Now, what's the final part of my talk is, what's the new frontier? Well, I think the new frontier, for me at least, has been helping to develop the global observation of the Anthropocene from space. This builds on the fantastic work from ground, ship and airborne. But the unique thing about the going to space is that we get global pictures. So here's this very nice blue marble picture of the Earth. I think that was from Apollo. And I just want to remind you again that humans have had this huge input on since the Industrial Revolution, arguably since the Neolithic Revolution, and we're really on a runaway train basically, and we're expecting this to keep going. But I think that the boat is to some extent full, and we think now, as I said before, that we're in this Anthropocene and we're seeing impacts of mankind globally. So pollution has changed from being a local phenomena to being a global phenomena. If we want to measure from space, we'd like to measure everything. This puts off agencies. We'd like to measure short-lived species like radicals and long-lived species. Essentially, the problem is the same. It's making measurements of small changes on a large background or small changes on a zero background. And if you look at the mixing ratios here, you'll see that some species are quite good at telling us about transport. CO is transported around, for example, from biomass burning in South America to Australia, or from Africa to Australia. These things were unbelievable when they were first seen. Only in 1990 or 84 or 94, we got the first 2 measurements of globally from the space shuttle of CO. So we need to know these things, and we'd like to actually have a system which comprises GEO and LEO, because we also have diurnal variations. The thing about a sun synchronized orbit is it comes around at the same time once per day, twice if you include the night. For solar measuring people like myself, it's only once a day. If you measure from geostationary, you can actually get diurnal variations, and that's what we need. We need a combination of both. And the timescales here, probably in the stratosphere, once, twice a day is enough. When you get into the troposphere, as we know from weather forecasting, we need all of these times. Okay, it's been a tough struggle. The good answer is that we've got a system. Unfortunately, it's not moving ahead as fast as we'd like to. In 1984 or so, in Max Planck, together with Paul Crutzen and Dieter Perner, he said this idea of DOAS, differential optical absorption spectroscopy, should work from space. And we then started to try and get this up. And you have to be persistent in this business. But we've actually had some good successes. But it took us 6 years from winning a proposal to getting the first one up. We proposed in 1998 Geosciences, which is going to be realized as Sentinel-4 in Europe, but that won't be before 2020. So the timescale for process, I don't think it's moving. I don't think we're data rich, I think we're data poor. Okay, this is anyway what we do. And I'm going to focus a little bit on the nadir, but we also need vertical profiles. And what we can do is look at the scattering. This is one particular way of doing it. We're looking at, again, spectroscopy of species which are electronic. Molecular spectroscopy is electronic transitions and overtones and combination bands. Okay, we've got this record in nadir. I'm just going to throw a few examples. This is the ozone hole as seen in nadir from the Antarctic, very stable, going up and down, modulated by the dynamics, which I talked about before. Okay, you can actually put this on a line, and the amount of energy, the simple message from this take-home picture is, from this message by Mark Vega from my lab, is that if you transport more energy to the polar vortex, it's destroyed more quickly, and you remove the conditions which are favorable to removing ozone. And in fact, all the years fit on the same line. That's a remarkable empirical discovery. What about into the troposphere? We're very interested in NOx. It's a perfect, so sorry about this fast now. We've got all these sources, fossil fuel combustion, bugs, and the rest of it. This is what we see from space. And you immediately see pollution. You can see a shipping line there. I actually think you can see roads over here. I think that's the I-70. You also see outflow from continents. You see a whole host of different things. If you actually average up now, and we showed this first a few times a year, look, this is now different parts of the world. If you take China, you can see it's really going up. It may be now, we're just talking about this in research terms, it may be now sort of reaching a maximum. It wasn't much impacted by the recession. Okay. Similarly here, I think that's the Middle East. and India are going up very quickly. In Europe, in comparison, in the US, we're seeing, compared with 1996 when we first started to make the measurements, that things are going down, but are probably flattening out and maybe increasing a bit now. So legislation has worked, but it hasn't worked, and we're not quite sure why it hasn't worked better than it should have done. But these are excellent measurements which are testing our understanding of these things. Just take India as example. I put this extra in because in my talk the other day I maybe implied we can't do cities. We can. This is work by Hilbel and Richter. And look, it turns out that India is fantastic to observe because we've gone from a rural economy essentially to an industrial one over the last 20 years. Look at this, 10% increases per year. It's unbelievable. No wonder they've also got pollution problems. What about SO2? We can see this for the first time. So we've got these sources, primarily combustion of lignite, sulfur-containing oils, etc., is the human modification of it. And this is what we see from space. Forget the South Atlantic anomaly, which is a bit of a pain at times for instruments. But we're seeing pollution and we're seeing volcanoes. Volcanoes are much easier to measure, actually. We get good information on them. But if we now just take China, this is the impact of legislation prior to the 2008 Olympic Games. This is NO2, which wasn't much affected by it, but descrubbing of sulfur seems to work. Okay, finally, I hope I'm now at the end, I'm going to nip forward. We also amazingly saw shipping NO2. You can see these shipping lines rather brilliantly. We can actually even see, I'm not going to show it now, but see the impact of the pirates on the shipping around the Horn of Africa. It actually, so we've started doing social science work, okay, in line with Future Earth. Anyway, we see basically what we expect increases. This is a whole future. This is a bigger effort from my research team, but basically I'm just showing that you can see it and we can see increasing. We need better measurements in the future. We can also see CO2 and methane. These are measurements over the world, but I'm focusing on the land. This is our record, and we're seeing increase in methane in the last years, which are not understandable. This has been seen from the ground first, but we're seeing it from space, and we're kind of filling in the holes between the very excellent ground-based measurements of CO2 and methane. And we actually think maybe, and others too, that fracking may be playing a big role, or emissions from fracking. We'll see. That's an open debate in the literature. Okay, for the future, we need much better. One of our proposals is CarbonSat, which has much better resolution. This is Saimaki World, this is what we want to go to, and this is Berlin. So we want to actually measure at the local area. Okay, we want to be able to say the difference between this island we're sitting on and downtown Austria. We can do it, the technology's there, we just need the money. Okay, and we need, and it's cheap compared to its Bargate basement giveaway. Okay, so what we actually want is a constellation of these things and get 1 kilometer or 2 kilometer every day. And we're prepared to use the ISS. Let's give the astronauts something useful to do. Okay, make it an observatory. They're very nice. I've met a few of them. They're very nice. They really love this type of stuff. We need to give them, you can put 34 instruments on the ISS. We can do lots of great stuff from up there. Okay, I have finished now. I'm sorry, I'm a bit late. Thank you very much. I think we've had a great pioneering age. We've come from the birth of the planet to the Anthropocene. We urgently need a system which is adequate to meet this, and we need these the ability to measure hotspots, to measure the true impact of man on this whole system, including the surface. We're very interested in surface remote sensing as well, of course. Finally, let's use the ISS, and I hope, might be a few typos in this, that we move from being hunter-gatherers to guardian of the planets. Thank you very much.